All right. So first thing, feeling generous, and so we'll go over a little bit of kind of where we left off, thinking about the distribution of sample means, but we're going to switch it to looking at sample proportions. We're then going to start talking about confidence intervals today. So the homework was supposed to be due Wednesday by the end of the day. I'm going to push it off to Friday. I think the last one question or two questions are going to be stuff that we go over today. So I'll kind of push that to Friday. That Learn Smart assignment is still, I want you to read that before class starts on Wednesday, okay? So that Learn Smart, I still want you to get on and get that done before we start class on Wednesday. But the Connect assignment, I'll push to Friday, being due at the end of the day, okay? Give you a little bit more time to work on that, and hopefully you've started that, that Excel assignment, at least worked on that first problem. This week we'll start talking about confidence intervals, so as we progress through the week, you'll start to be able to work on the second and third question for that Excel assignment, okay? Other than that, let's see, where's the chat? There you go. Any questions for me before we kind of get going here? Okay, all right, so hopefully it's been a little bit over the weekend. So last class we left off talking about the distribution of sample means, right? And we said we know the distribution of sample means will always be centered or have a mean that is the population mean. We walked through kind of that data exercise to prove that. We also said we know the standard deviation is always going to be whatever the population standard deviation was divided by the square root of n, right? Or, kind of set this up, what we had was the mean of my sample means was equal to the population mean, and the standard deviation of my sample means, we said there's really two ways to write it. Both ways mean the same thing, just a little bit rearranging that mathematically. Okay. We then said that z-score we could use for any value of the sample mean we were interested in was take whatever cutoff value we're interested in for the sample mean, subtract, right, the mean of my sample means, divide by the standard deviation of my sample means. Now we could go ahead and plug this in. We know the mean of the sample means is just my population mean. And we know the standard deviation is going to be equal to one of these equations, right? So we could go ahead and plug that in or calculate the intermediate step, right? Calculate this first and then plug it into that denominator, okay? So with that in mind, we can do the exact same thing looking at what we'll call sample proportions. So all a sample proportion is really the sample mean of a 1-0 variable, right? So if we go back to the binomial distribution, and we remember there we were looking for the number of successes, say, out of 100, right? We said the mean would be equal to this equation, the variance is equal to this equation. Well, that was giving me the number of successes out of 100. If I wanted to turn that into a proportion, right, so that's between 0 and 1, right, or a probability, well, if this is the number of expected successes, to turn that into the probability, I would just divide by whatever my trials was. So if I divide both of these by n, when I'm thinking about my sample proportion, right, not the number of successes, but the proportion of successes, if I divide this by n, I just get whatever the true population proportion is. And if I divide this by n, I would just have p times 1 minus p. But we know that for the variance of a sample statistic, right, like the variance of the sample means, let me have this up while I'm talking for the video. Right, the variance of our sample means, or the standard deviation of our sample means, we had to divide the original variance by our sample size. So if I divide this by n, p times 1 minus p, I then have to divide it by my sample size again, right? When I'm thinking about the variance of my sample proportion. Okay? So if this is the variance of my sample proportions, and here's the mean of my sample proportions, well, it's just like what we were doing before. So, try and make the comparison here. So if we have the z-score for our sample means look like this, all we're saying is for the sample proportion, well, now we're looking at cutoff values not for the sample mean, but for the sample proportion. and we're going to subtract the mean of my sample proportions and divide by the standard deviation of my. It's the same exact thing we were doing before. Anytime we want to find a z-score, we look at whatever statistic we're interested in. We'll have different cutoff values for that. We'll subtract the mean of that sample statistic and divide by the standard deviation of that sample statistic. Well, here we know the mean of our sample proportions. Once we go back to the slides, kind of have a reminder. Well, that was just going to be whatever the population proportion was. And if we wanted to, we don't have to calculate it in the intermediate step. We can plug it right into the equation. The standard deviation of my sample proportions is the square root of p times 1 minus p over my sample size. Now this denominator still represents the standard deviation of my sample proportions. Just like before, we could have rewritten this as right? This just represents the standard deviation of my sample means. Right? So we could plug everything in and just do one equation, or we said if we know this is the equation for the standard deviation, we could calculate that first and then just plug that value into the denominator. Either way is fine. And we worked through a couple examples last class for the sample mean. And we'll do the same thing. We'll work through a couple examples, and I'll show you how you could do it both ways, either calculating the intermediate step and plugging it in, or just doing it as one equation. Right, we'll go through a couple examples and I'll show you both ways there, okay? But really it's the same thing. We're still interested in finding what's the probability, given that this is kind of the true population proportion, that I saw the sample proportion that I did from my sample of size n or anything below it, right? Because once I turn this into a z-score, well now I just go to the tables and I can find the probability that I saw something that was equal to that value or lower. Once I get that z-score, all the steps are the same as what we were doing last week, right? It's just that now we have a slightly different equation for calculating that z-score, right? And I say it's different. I mean, it's still the same setup, right? Because this represented the mean of the statistic I was interested in, and this denominator still represents the standard deviation of the statistic I'm interested in, okay? So, I want to show you one more thing, actually. Let me think of what data set we had that had a 1-0 variable. I know I've got some old stuff, so let me go here. There's some GPA data somewhere, not in here. There we go. So if I did have a variable that was 1-0, so right here, you guys won't have this data set. I'm just going to kind of show you. I just want to be able to give you kind of a visual of what we're thinking about. Let's say I had a variable where it was a 1 if this individual, so this is like college GPA scores and different information on students. It's a 1 if they're female, 0 if not, right? So I could find the proportion of females from this sample by simply using that oh my gosh, hit my caps lock. There we go. Simply taking the average or finding the mean of this 1-0 variable. If I do that, I'm going to get 0.4496, or about 45% of this sample is female, right? And the reason why that works is because if I think about what I'm doing, when I'm taking the mean, remember the mean was just add up every single observation's value for x and divide by the number of observations I have. Well, for that 1-0 variable, every time I see a female, it'll be a 1, and then maybe the next 2 observations were male, the next 2 were female, so on and so forth. Well, all this numerator is going to do is count up, right? The zeros don't change it at all, so it's just going to count up the number of females in my sample and divide it by the total number of observations. So it's going to give me the proportion of that sample that was female, right? But it's really still kind of like a sample mean, because if we just find the mean of a 1-0 variable, it gives us the sample proportion, okay? So it's a little bit unique because, you know, the variable is 1-0, but just think about it, we're still finding a mean, right? So let's work through an actual example here. I just want to kind of reiterate that point. Oops, there we go, all right? So I did kind of this on the board, but eventually we can break this down where if I know the mean of the sample portion, I know the variance, I know this equation will be my z-score equation, okay? So let's actually apply this to a problem, okay? one thing to remember, I want to mention, we also still have to make sure the central limit theorem holds. I still need to have a number of observations over 30, okay? So maybe the setup is, what's the probability that if I flip a coin 100 times, 55 or more of them, right, come up heads? Okay? So the sample proportion, or the cutoff value I'm interested in, would be what in this problem? Remember, proportions, right, somewhere between 0 and 1. So what cutoff proportion am I interested in here? 55 or more heads would be a proportion of 55 out of 100, 0.55, right? So the setup that I want to be thinking about is, well, I have what? I'm flipping the coin 100 times. N's definitely over 30. So the central limit theorem is going to hold. So what I know is going to be true is the distribution of my sample proportions, just like for the sample mean. Remember, the sample proportion is just the mean of a 1, 0 variable. They'll be normally distributed around whatever the true population proportion is. Well, for a coin flip, what should that true population proportion be? Yeah, just 0.5, right? We want to be careful here when we say things like 50, right? 50%, but we're dealing with portions, should be between 0 and 1, so 0.5. Right? We wanted to know the probability of seeing what? 0.55 or greater. So automatically, we know that this probability should be less than what value? The area to the right of the mean would be 0.5. So we want something smaller than that, so it's going to be something less than 0.5. How do we actually find it? Well, we can convert that value of 0.55 into a z-score. Okay? How do we do that? Well, we just have that equation, right, that I just kind of shown you. Right? So once I turn this into a z-score, I want the area to the right. I can look this up in the table. It'll tell me the area to the left. I then subtract that from 1. Okay? Right, because remember, the original problem started at 55 or more. So we're wanting the area to the right there. Okay? So I'm going to erase this for a second, keep the z-score down there. So the equation that we had, I think this is running out of juice, so let's see, hopefully this shows up pretty well. It's not that. So the equation that we had, and we can do this all in one equation, and then I'll do it again and show you if we did it the intermediate way. We can take that sample proportion cutoff value that we're interested in. We can subtract whatever the true population proportion was, which is 0.5, and then divide by the square root of the population proportion times 1 minus the population proportion divided by my sample size. And I'll show you that formula again here in just a second. I'm just plugging R values into it. Remember, this denominator, the entire thing just represents the standard deviation of my sample proportions, okay? So, once I get this plugged into my calculator, it's going to return to me some z-score. I can look that up in the table. The table will tell me the area to the left of that z-score, or the probability I saw that z-score or something below it. I wanted the probability that I saw that or something larger, so then I'm going to subtract it from 1, and now I'm done. Right? So, I think I have the other way in the slides here. So if I plug everything in, I get this z-score of 1, okay? So if I'm thinking down here for the video, right, this z-score, we just found is 1, okay? So I'm going to look that up in the table, the standard normal distribution, or the z-tables, if I can get it to, there we go. So I had a z-score of 1, scroll down here, 1.00, 0.8413, okay? So the area to the left here, 0.8413, I wanted the area to the right, so I subtract that from 1. I get about what, 0.1587, right? So another way I could have done this, right, where did I put that? Oh, that fell. Another way I could have done this is if I know that denominator is just the standard deviation of my sample proportions, I could have found that first, where I know the equation for the standard deviation of my sample proportions is the square root of p times 1 minus p over n. Our n was 100. Our population proportion was 0.5. I think this is what? So we got what? 0.5 times 0.5 divided by 100, square root of that. This should just be 0.05. Okay? Now, actually, I could have known this without using that formula if I remember something. What does a z-score represent? It's the number of standard deviations away I am from the mean. So remember, I was looking at that cutoff value of 0.55. It was 0.05 away from that population proportion, and the z-score was 1. So I knew that 0.55 was 1 standard deviation away from the true population proportion. Well, if it's 1 standard deviation away, right, and it's 0.05 away from that population, well then, yeah, the standard deviation had to have been 0.05. Okay? Now, I would never expect you kind of to work that way and back it out, but remembering what that z-score represents, I kind of wanted to talk through that. Okay? Now, here, if I did the intermediate step and first calculated that standard deviation of my sample proportions, now in that denominator, all I have to do is plug in that 0.05. Right? So whichever way is easier for you to think about. If it's easier for you to look at that and say, well, I know this is the formula that gives me the standard deviation of my sample proportions, I'll deal with that first, then I can plug that into the denominator, that's fine. If you want to like put it, basically plug this equation in and do it all as one equation, that's okay too. You'll get the same answer, right? You'll get the same z-score of 1, and then from there it's the same steps that we've been doing at the last kind of couple class periods, right? Once you have the z-score, you go to the tables, you find the relevant probabilities, and then sometimes we have a little bit of extra work to do, like here we had to subtract it from 1 because we wanted that area in the upper tail, or sorry, to the right of that z-score. Any questions on that one before we kind of keep moving here? Is this kind of connecting what we were talking about last class? I want to try to make that connection so it's not like we're not doing something completely new. It's just a little bit of a change, okay? All right. So I've got one more example for that, and then we'll introduce the idea of confidence intervals. Oh, maybe. Did I not get my... There we go. So what if I wanted to do the probability of getting 66 or more heads out of 144 coin flips? Right? Well, this is where right away, let's just draw it out, and we can probably get rid of some of these answers pretty quickly, okay? So what are we looking for here? We have 144 coin flips, so we definitely know the central limit theorem is going to be met. Our sample proportions should be normally distributed. And here, once again, it's an easy one with a coin flip because we know the population proportion will just be 0.5. Okay? I want 66 out of 144. Right? So I can think about what's the cutoff value I'm interested in. 66 out of 144, or what? 0.4, approximately 0.458. Okay? So I'm thinking about what's the probability that I see the proportion of coin flips out of 144 be 0.458 heads, or 46-ish% heads. And actually, I forgot, was it more or was it less? In the slides, let's see. Or more, right? Okay. So if we want or more, we're thinking about the area to the right. Right away, I know that probability has to be greater than what value? 0.5, right? Because the area to the right of the mean is 0.5, I want something larger than that. So right away, when we look at these possible answers, remember, like on the exam, I'm going to be a large majority of it multiple choice. This really helps me not make easy mistakes, okay? So right away, I know it can't be 0.3, can't be 0.15. I know B or D is going to be the answer here. Now, I don't know, from here, I can't choose without actually working through the problem, right? So let's keep going. So I want to turn this value into a z-score and then find the area to the right of it. So we have that z-score equation. The first thing we had in there was what the cutoff we're interested in, so 0.458. Subtract whatever the mean of the statistic you're looking at is. Well, our mean is 0.5, or our population proportion is 0.5. Then here we divide by the square root of that population proportion times 1 minus that population proportion over our sample size, which is now 144. Oops. I'm not sure if this will be on the video, so let me move this out of the way here. So at this point, it's just a matter of getting this entered into our calculator. Right? At this point, it's a matter of getting that entered into our calculator and finding out what that z-score is. Okay? Now, I could have done this by first finding this and then just plugging that number into the denominator. So if I do that, just so you have numbers to kind of check this. 0.042, approximately 2. Right? Now, this is one of the problems if I do the intermediate steps. I'm just writing numbers down so you can see them. You want to use like the actual value in your calculator, right, because it stores it out to more decimals. Right? But once I have that, right, I can plug that into my denominator, find my z-score that way as well. If I do that, I actually end up with -1, okay? So if my z-score is -1, the next step is I need to go to my standard normal table, and it will tell me the area to the left of that. Or, said differently, the probability that I see a proportion of coin flips that is what, approximately 46% or less, right? Because remember, the table always deals with the left side. I want the area to the right, but the table always deals with the area to the left. Okay? So I go to my table, look up that z-score of -1.0, scroll up, 0. So -1.00. The area to the left of that is 0.1587. So I know that this area is 0.1587, but I wanted the area to the right, so the only other step I have to do is what? Yeah, subtract that from 1. All right? I should get that 0.8413. Okay? Any questions on this before we keep moving? What if I just wanted the probability that it was less than 66 out of 144 coin flips? Everything would be exactly the same. I just wouldn't have to do that last step, right? Because the table would automatically give me the area or the probability that I wanted. Okay? Any questions on this before we keep moving? Really gonna switch gears after this. So if you have questions over these types of examples, ask them now. Okay? We're okay with this? Okay. So maybe, there we go. So at this point, we've talked about, we're dealing with sample means and sample proportions. Okay? And we had this other discussion about making sure our samples were unbiased, right? Or looked a lot like our population to make sure that we can't usually observe population parameters or population means, population proportions. Like with a coin flip one, it's easy because I know what a coin flip's population proportion is. If I think about what's the population proportion of, I don't know, females in the entire population of the US, I know it's around 0.5, but I don't know the exact population proportion, right? Without looking at some data, or if I don't have the data collected, I just won't be able to know it, right? But what I can do is I can take a sample and hope that my sample gives me a pretty good idea of what that population parameter is, or what that population mean, or what that population proportion is. So I'm going to this discussion today, I'll probably continuously refer to the population mean and sample mean, but really it's any population parameter we're interested in. So everything I say about the population and sample mean would be true for the population and sample proportion as well, okay? And I think Friday, I don't know if we'll get there Wednesday. Friday, we'll for sure start talking about confidence intervals with proportions. But everything I'm gonna be saying now, I'll say in the context of means, but it would apply to proportions as well. So 99% of the time, we don't know the population mean. So we hope that our sample values are good predictors of it. Right? So what are the things that we care about when we're trying to make predictions? Well, first of all, we had a discussion. We want to make sure these are unbiased samples, right? Or unbiased predictors of where that true population mean is. We also want to make sure that that sample mean has a really, really small a small variance if we can, right? And I kind of showed you this a little bit last week, but the idea there is, if I take higher sample sizes, we said what happens to the variance? Well, remember, the variance of our sample means is just the variance of the data we're sampling from divided by the sample size. So if we take high samples, we get a really, really low variance. Well, why is a low variance good? Well, because if I can get a low variance, when I think about the distribution of my sample means, it's going to be really, well, I should probably over-exaggerate this. Hold on. It's going to be really, really peaked right around whatever that population mean is. So I know that values really close to the population mean will be very likely for me to see from if I only take one sample. I'm only taking one sample. So I'm hoping that when I take one sample, the probability I see values near the mean is really high. Probability I see values very low from the mean will be very low. Right? That way I'm trying to guarantee that that sample mean is going to be pretty close to my population mean. Right? You know, if I think about instead, let's say I had like a really high variance, so a really flattened normal distribution. Well, now seeing values really close to the mean is almost equally as likely as seeing values far from the mean. So my sample is not going to be very reliable. Right? So that's kind of the two things that we care about there. Right? So what we're going to do is we're going to say, look, all I can observe is the sample mean I see from the one sample that I take. Right? Now, I'm going to then say, okay, look, I'm going to use what I found from my sample, but I'm going to give you a range of values that I can say with 90% confidence, the true population mean is somewhere in between this range of values based off of what I saw from my sample. Okay? So we don't know, where it's at. We take a sample. We're going to want to give a range of possible values with a certain level of confidence that the true population mean is somewhere in this range of values. So maybe if I'm thinking about income, I take a sample. I see that the sample mean is, $45,000. I then might say, well, look, I know that even if the true mean was 50,000, I could still see 45,000 if I took like a sample of 40 people, right? Maybe I have a couple people that are lower, right? I just ended up with a couple people that have lower incomes in my sample. But I know that it's probably, if I see 45,000 for my sample mean, the average income probably isn't 240,000, right? I know my sample mean is going to be a little bit off from what the true value is, but not way far off, right? And so maybe if I see 45,000, I think, well, could be a little bit off the true population mean, so I'm going to give myself some buffer, right? I'll tell you, well, based off what I saw from my sample, $45,000 is the sample mean I see. Maybe I'll tell you, well, with 90% confidence, I feel okay telling you that the true mean is anywhere between $40,000 and $50,000, right? That way, even if my sample mean was a little bit off, the population mean is probably somewhere within $5,000 of it, right? But how do I choose kind of what that lower and upper bound of my range were, right? So I also kind of to mention, I'm saying like, I want to be able to say this with 90% confidence, 95%, 99%. I could say it with 80% confidence, right? How do I choose kind of what level I want? Usually that's something that's given to us, and we'll get into that more probably not until, let me see where we're at. Yeah, probably not until Wednesday. But this idea that I want to choose some value to go below and above whatever that sample mean I see is, and then say, okay, within this range of values, I can tell you with 90% confidence, I think the population mean is within this range. Right? So in my example, I said the sample mean we saw was 45,000. I just chose, at random for this example, just to kind of set it up, I want 5,000 below the mean, and I want 5,000 above the mean, right? Went to 40 and 50,000, and said with 90% confidence, based off the sample mean I saw, the population mean's probably in between 40 and 50,000. But how did I choose W, or how should I choose W? I did it not, I didn't do it the correct way in this setup, but there is a way in which you can guarantee that you can say something with 90% confidence if you choose W following a certain procedure, a certain kind of steps. Right? So we're gonna have to go back a little bit. One thing that's really helpful in being able to choose what that W is that I want to go above and below that sample mean I saw is that we know the sample means are going to be normally distributed. Okay? So if I know the sample means are normally distributed, I can think about something like, if I wanted to say something with 95% confidence, if I wanted to give you the 95% confidence interval for what the true average income in the US is. Well, if I see a $45,000 for my sample mean, how do I choose that W? That would give me 95% confidence that I could say the true mean income is somewhere in between this range. Well, if we go back to last chapter, or kind of last week, we know that if I go 1.96 standard deviations below my true mean, the probability I see something further than that away from the mean is 0.025, right? So how do I know this? Well, remember, if I look at this table, if I go to -1 point, let's see if I can get this all on the same thing here, just barely, right? So if I go to -1.96, I know the area to the left of that is 0.025. So what that's telling me is, if I see a z-score of -1.96, right, the probability I see a z-score of -1.96 or anything lower is 0.025. Or kind of the visual there is the probability from that standard normal distribution, probably I see a z-score of -1.96 or anything below it is 0.025. Okay? If I see anything that's 1.96 standard deviations above the mean, or anything further away in that direction, what should this area be? What's the probability I see something 1.96 standard deviations above the mean or greater? Well, the normal distribution is symmetric, and it's centered around 0. Remember that the z-table, or the standard normal distribution, has a mean of 0. So this should fold on top of itself. If the area to the left of -1.96 is 0.025, the area to the right of +1.96 would be what? 0.025 or 2.5%, right? If this folds on top of itself, then every value we see, the positive and negative, the area to the right of the positive would be the same as the area to the left of the negative value. So what that's telling me is the probability I see something in between 1.96 standard deviations away from the mean, because remember, these z-scores, the interpretation is the number of standard deviations away from the mean. So the probability that I see something 1.96 standard deviations away from the mean in either direction, or closer to the mean, would be 0.95 or 95%, right? We're trying to build this 95% confidence interval. Okay? So I know that 5% of the time, I'll see something in either direction that's more than 1.96 standard deviations away from that true population mean. Okay? So we're going to kind of use that kind of reminder and then go a little bit further. Right? So we know that the probability that we're 1.96 standard deviations above the mean or more, or 1.96 standard deviations below the mean or more, both are 0.025. So the area that's, say, not in the tails, right, this blue area, is going to be 0.95. Okay? So how can we use this to then build what our confidence interval should be? So what we're going to do is we're going to take that sample mean. We're then going to go 1.96 standard deviations above and below it to get our lower and our upper bound for our confidence interval. Okay? So if I go 1.96 standard deviations above and below, that's how I'm going to build that confidence interval for my sample mean. Okay? Now, what ends up being true is, if let's say I take one sample, right? I can't actually observe the population mean. But let's say we had this weird scenario where I have the actual population data, kind of like that birth data, so I can see the true population mean. And then to prove this to myself, I start taking samples. So I take one sample, right? I see this is my sample mean. I then go 1.96 standard deviations above that sample mean to get my upper bound. And I go 1.96 standard deviations below my sample mean to get that lower bound. Well, notice for this sample mean, my confidence interval would include the true population mean. I take another sample. Maybe I see this as my sample mean. I do the same thing. Go 1.96 standard deviations below, 1.96 standard deviations above that value. Notice this confidence interval also includes my population mean. And I try to draw these to scale, right? These should be the same length, right? Because even though I'm starting off at a different sample mean, 1.96 standard deviations is always going to be the same value. Okay? Now the problem is, if I see any sample mean that's in this blue range, the confidence interval will always include that true population mean. But 5% of the time, I'm going to see something out here. Now, if I were to see this as my sample mean, well, I can kind of see here, it's a low probability that I do see that, right? But if I did have that as my sample mean and I built my confidence interval, it would not include that true population mean. So what's going to be true is if I see any sample mean that's in this red range or more than 1.96 standard deviations away from whatever that true population mean is, my confidence interval for those values wouldn't include, right? This doesn't quite include the true population mean. So if I took like an infinite number of samples, 5% of the time when I build my confidence interval, I'm not going to be actually capturing the true population mean. Now, 95% of the time, I'm going to see a population mean, I'm going to see a sample mean where the confidence interval does include that true population mean value. Okay? So this is the idea behind what we're doing, right? So we use the idea that we know that these sample means are normally distributed. And so we know that if we would go 1.96 standard deviations above and below, that would give us kind of the probability of seeing something within that would be 0.95. Probably we see something even further would be 0.05. We could do this for any level of confidence. If I wanted to do this for, say, let's say I want to do the 90% confidence level, right? I would say, okay, if there's 90%, I want to find the number of standard deviations I can go above and below the mean such that the probability I see something in between those values is 0.9, right? Or representing the probability of 0.9, 90%. Well, if I know that the area in between these two values, right? Actually, I'll draw this instead of use this one just so we don't confuse any of the numbers. Let's say I think about my standard normal distribution and I say, look, I want to choose, right? Or I want to find the number of standard deviations I can go above and below the mean such that the area in between these two values would be 0.9. Well, if there's 0.9 within that, what area has to be in my tails here combined? The area in between these two values is 0.9, right? What area has to be outside those values? 0.1, because the area under the curve is 1. So the total area has to be 0.1. But remember, we're looking for the same number of standard deviations above and below. So these areas should be exactly the same size. So if the total area is 0.1, what area has to be in each tail? Yeah, 0.1 divided by 2. So I know I want the z-scores such that the negative z-score gives me 0.05 in my lower tail. So then what would I do? I go here, go to my table. I say, okay, where's 0.05? Well, I can get pretty close. So in between negative 1.6, negative 1.65, take the higher of the two, negative 1.65, or, that's not what I wanted to do. If I went 1.65 standard deviations above and below the mean, I know the probability I see something in between 1.65 standard deviations above and below the mean would be 0.9. Right? And really what I'm saying, that's my z-score. So what I'm really saying is to get my lower and upper bound, here I'd want to take whatever sample mean I see to get my upper bound, right? This is just a z-score. I want to turn this into an actual value for the original variable x I was interested in. So to get the upper bound, I would add 1.65 times the standard deviation. Now remember, we're looking at sample means, so it's the standard deviation of my sample means, right? Then to get the lower bound, I would subtract or go 1.65 standard deviations below that sample mean that I see, okay? So that's the general idea of what we're trying to do. Where are we at here? So got a little bit more time left. I want to get through a little bit more here. So we've got this set up. So one thing, just some kind of terminology here. When I say things with 90, 95, 99% confidence, those are usually our benchmarks. We use those a lot. 90, 95. Now we could do 83.2% confidence intervals if we wanted to. It's just that's kind of a weird thing to tell someone, right? It's a lot, our benchmark values would be 90, 95, and 99. Well, if I know the confidence level that I want, we're going to start referring to something called alpha, okay? Alpha is essentially, I think this is the easiest way to think about it. You can use this equation and back out, if you know what the 99% confidence level is, if this is equal to 0.99, do some algebra solve for alpha. But really, the confidence interval, right, tells you what percent you want in between your lower and upper bound for your confidence. Your confidence level tells you the percent you want in between your lower and upper bound for your confidence interval. Alpha is the area outside of that confidence interval, or the percent outside that interval, but in decimal form. Or, think about it differently, it's the area in your tails. So when I was looking at the 90% confidence interval, alpha was, we said 0.1, right? Because there was total in the tails of 0.1. We knew that meant in each tail we had 0.05. If we go back to the example where I was looking at the 95%, we could think about there, I'm looking at where is it? There we go. 95% confidence interval. What percent is outside the interval? 5%. In decimal form, 0.05. Or the total area in our tails here, there was 0.025 in each tail, which would mean the total area in the tails is 0.05, and that would be our alpha. So alpha is the area in our tails, or it's the percent outside the interval, but in decimal form. Both those are good ways to think about it, right? The first way is probably a little bit more technical. The second way is just an easy reminder, right? If I want the 95% confidence interval, what percent's outside the interval? 5%. Decimal form of that would be 0.05. Or if I want the 95% confidence interval, the other way to think about it is I know that there's 0.95 in my interval, which means the total area in the tails outside the interval would be 0.05. Okay? So alpha is kind of that total area in our tails. So when we knew that we had, and you can kind of work the other way too, right? If I know alpha is 0.01, that means the area outside the interval is 0.01. That means the area inside the interval is 0.99. But as a percentage, 0.99 would be 99%, right? So we can work in either direction. Now, when I'm building that confidence interval, remember, when I had a total alpha or total area in my tails of 0.1, I had to divide that by 2 to get the areas that I wanted in each of my tails, right? We took 0.1 was the total area in the tails divided by 2, because we had 2 tails here. So you can think about this as, this was alpha over 2. What did we then do? Well, once we knew what that area in the tail, alpha over 2 was, we looked up the z-score that would give us that. Okay? So the actual equation, when we write this out, is going to look something like this. Right? To build our confidence interval, we're going to go whatever number of standard deviations away from the mean, that's the z-score, would give us alpha over 2 in each of those tails. Right? That's how we looked up that, when I walked through that example, that's how we found that z-score of negative 1.65. So you'll take whatever confidence level you're interested in, figure out what alpha is, You'll then say, okay, I know there's alpha over 2 in each tail. I'll look up the z-score for alpha over 2. Then I'll have to figure out what the standard deviation of my sample means is, plug in my sample mean. Now I can find my lower and upper bound, right? Now to find the standard deviation of my sample mean, just kind of as a reminder, let me see. I don't have it up here. So just as a reminder, that was where we said the standard deviation of my sample mean is the square root of whatever the original variance was over my sample size. So once I take my sample, I'll know my sample size. For the sake of what we would have to be told or given what that population variance is, right? And then of course, when we have a sample, we can also calculate the sample mean. So we would then have all the components we need to kind of plug in for these two values. And then it's just a matter of looking up the z-score for whatever confidence level you want, okay? Let me think if there's anything else I want to say. Are there any questions at this point? Is this kind of following along with me somewhat? All right. So, go over something kind of quick, and we'll probably revisit this at the beginning of the next class. But what is going to change our confidence interval? We'll think about it this way. If I want to say something with 90% confidence, right, then I might construct this confidence interval, I don't know, that starts and stops at 5 and 10. Well, what's the only way I can tell you, if nothing else changes, like if I don't take a different sample, I'm dealing with the same sample, how can I give you a range of values that I could tell you, not with 90% confidence is it between these two values, but 99? Well, what do I have to do? I have to include more values, right? If I can make my confidence interval wider, right, well, then I can say things with a higher level of confidence, right? Because if I know that 90% confidence, I can tell you it's in between 5 and 10. To tell you with 99% confidence, then I, would have to kind of widen that range, right? Otherwise, if I gave you a smaller range and I told you with 99% confidence it's in between these two values, well, then how the hell did you tell me with 90% it was this wider range? It doesn't make any sense. Right? So we're going to think about what changes kind of the width of our confidence intervals. And whatever changes the width of our confidence intervals, right, is going to change the kind of the level of confidence that we can say. Right? So I actually think I'll end there. Yeah. So there's multiple things that change, right? I was kind of bringing up one, which is that if we change the level of confidence we want to say something in, we can widen and shorten it. There's going to be two other things that change as well. So we'll end kind of a precursor to the next class. We'll end in this because it's a good question. The variance is going to matter, right? Because the variance is floating around in here. What else is going to matter? The sample size. Okay? So we'll go through the beginning of the next class, talk about how there's three things that can change the width of our confidence intervals, right? Which is helpful because if we can get a really small confidence interval, but I can still say something with 99% confidence, well, that's great. I've just narrowed down the range of values I'm telling you the true population mean is. Okay? So we'll pick up on this next class. We'll work through a few examples, and we'll probably do a little bit of Excel work as well. I'll show you how we can do some of this confidence interval stuff in Excel. Okay? But that homework has no confidence interval stuff, that Connect homework. So I'll send that due date to Friday. Make sure you kind of get that done, and get that Learn Smart done before the start of next class on Wednesday. All right?